Welcome everybody to this week's episode. Before we get into the actual episode with Zack Wolske, we have a little bit of an announcement to make. Basically, I know we've been talking about this for a really long time, but the merch website is done, but
Indeed.
We are just figuring out details with the shipping arrangements because we will be shipping to every single country. Essentially, I don't think it matters, to be honest. So we're just gonna figure out all the shipping stuff, and then we're gonna hit publish on the website, and you guys can go and buy some merch if you feel like it. Also, how it's going to go down is basically we're going to open up orders for like 2 weeks or a month, depending on how many orders come in. And then once the ordering period is over, we're going to send in all the orders, get them made, get them shipped out. And if it's a high demand, we'll do it again for basically infinity amount of time. However many people want shirts, you can get a shirt. Just you can go and order. There's no like limited supply.
We also now have a Discord server that seemingly a lot of people enjoy.
Very true.
You can talk to us personally. We also have a physics questions chat. If anybody wants to just talk physics, you can do it there. It's posted in our link in our Instagram bio. We might do it in this YouTube description as well.
We'll put the link in every single YouTube video / Spotify description from now on. And we might do some like live Q&A voice chat with you guys if you guys are online. So
Also, a lot of people asked about different colorways in the future and whatnot, and obviously depending on demand, like it's all available. Like these shirts look sick. They feel great. I think from
highest quality in the world.
It's legitimately. I mean, I don't know about that statement, but it's legitimately a really good quality shirt.
Yeah.
So
embroidered. As well.
All embroidered, like really high quality, like from a shirt factory. I mean, I don't know where else people get it done.
I don't know.
So I mean, all of that's really good. I don't think there's anything else before the episode.
So enjoy this episode.
Just like. We are recording this episode like a couple days right after the previous one. So no comment of the week or anything special like that. No change in our downloads or followers. So nothing crazy. When we get into the episode, we get into it. So hopefully you guys enjoy it. And
All right, see you there.
It's the language of the universe.
But I don't understand it.
Hello, everybody, and welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you to episode number 110, where today we have quite a popular guest back on our podcast. We have Dr. Zack Wolske.
Hi.
So, Zack, hi. How are you? How have you been? Maybe a little introduction to those few who have not maybe listened to any previous episode of you. Who are you?
Sure. So I did a postdoc in math at U of T, and I taught some courses. And Parker was in one of them, and then came on here and talked about, I think, number theory and some combinatorics.
Combinatorics, right. That was a sick episode, right? Yeah. There were a lot of, every time you come on the podcast, we always get our brains picked. So it's always fun. I think, I mean, again, all guests are wonderful, but this is actually like a level of us interacting as well, which is kind of interesting that we don't usually see. So for those of you listening to the podcast, go check out the YouTube video because there might be some more details that you might miss on the audio section. So just letting you know.
Oh yeah, there's pictures.
Right. Yeah. There's pictures. No.
So here we go.
We can just start up.
We're going to talk about group theory today. So I guess the most basic question. How would you explain group theory to somebody who doesn't know what group theory is?
Oh boy. I was thinking, let me go look at my old group theory notes. So I dug them up, and I think that's a really bad way to do it. We had like a mathematical definition, and there's a binary operation, and a set, and a monoid. And I was like, I don't know what these terms mean, and there's no way. I would say a group is some way of describing symmetries of an object. And a lot of things are groups. And you may not think of them as groups, but secretly they're groups.
And must they be symmetries, or are they any group that that represents anything?
I maybe have like a circular definition of symmetry, in
Oh,
that I would
yes,
say
okay, okay.
symmetry means a thing that a group is measuring. Like that, like
fine
that's
that way.
that's groups are the structure that we use to study symmetry. So if something has a symmetry, we would go, we can describe that with a group. It is kind of like algebra for equalities.
That's a nice way to put it.
Algebra for equalities.
Yeah, like algebra is the thing that we use
yeah,
to study
okay.
when
Sure,
equal things.
So like the the equivalent of maybe holding up a square and rotating it would be to put things on a scale.
Absolutely, yeah. So the scale is like algebra.
Yeah.
It does some powerful things, and you have to make sure everything is balanced nicely. And then group theory has more like picture type descriptions of things. Like if I want to think about, I have some square, how many different ways can I move this square around and make it still like look like the same square? And group theory will give a description of those actions and how you can compose the actions together. And if you want like a formal, here's how I would describe a group to someone who has some algebra background. It's a bunch of things that you can do where you can compose them. So I can do one thing and then another thing, like apply a function and then another function. And I can undo everything I did. So everything has to be invertible. So like moving the square around, if I give it a little clockwise turn, I can give it a counterclockwise turn. If I flip it, I can flip it again. And those are undoing the things. And if I want to compose, I can turn and then flip. And then that would be the same as first flipping and then turning, but the other way.
So what would be an example of something that's non-invertible?
Oh, things like multiplying, like, let me give you, if you take all the real numbers, except for 0, they're all invertible. So there's a group that is the real numbers with multiplication, except the number 0. You can multiply two numbers together, you get another thing, it's also invertible. You can undo whatever multiplication you did, and that's a group.
So the group of the real numbers comes with the operation of multiplying. Well, minus the 0.
Okay.
The element
So
0.
when you say the group of real numbers are also a group
Sorry, I didn't mean group.
using
I mean the
addition.
Set. Right. I meant the set of all real numbers combined with multiplication makes a group. Is that how you would say that?
The set of real numbers without 0.
Without
the set of
0.
non-zero
Right,
real numbers
Right, non-zero.
with multiplication is a group.
Nice.
Yes, that's exactly what I would say.
And what kind of symmetries does that relate to?
Yeah, we can think about this, right? Like, what can you do with this group? This group has a lot of automorphisms. It has
Which
a
means, sorry.
which means so a morphism is a function. It's a function that I'm going to do to the thing itself. So
Okay.
auto is on itself.
Oh,
So like, what can I do to real numbers? If I think about this whole like real line minus 0, it's not in there. I can like stretch it. I can take all the real numbers, multiply them all by 2. And now I get another copy of the real numbers again. Right?
Yeah.
So like
Yeah.
groups have this kind of a property. If I take an element in them and apply it to the whole group, I get like a copy of the group. And sometimes they have extra.
So like you take an element like 2 from the set of the non-zero real numbers, and then by applying that, the element becomes the transformation, and then you get the same thing back. Okay, interesting. And you could do that with any element in the non-zero real numbers, and that would also be an automorphism. Interesting.
so then what would be a difference between a group and a set? Because he was mentioning set, and
Well, the
you
group
were
has
mentioning
this-
group, and then you corrected yourself for set, and I'm like, okay, but why? Like, I mean, I understand there probably is just a definition difference, or is there something way deeper that I'm not understanding?
So I think he wanted to clarify the set of real numbers, and then we get to choose an operation on it.
Okay.
Right. So the
Right.
part that makes it the group is that we say what the operation is. So we could also have, if I take all the real numbers, including 0, and I make my operation addition, that's also going to be a group. Because I can subtract, that will undo everything, and I can add 2 things in a row.
So is this just a way, because what I've understood so far is that this is just a way of of simplifying things. Is it? Because a
It
group
could be making them more complicated.
You think so? Because I feel like if you take the set of things that you, like for example, if you want, I mean, you're mentioning addition, subtraction, I'm obviously thinking it can be way more complicated than that, right? If you have an invertible function or something and you want to apply it to whatever data, or I'm just spitballing, things on my top of my head, but if you were thinking about doing something like that, I feel like it could be,
Yeah, if you took all the possible invertible functions on whatever you want, that's a group.
Right, because you can apply it and you can go backwards.
And then you can, because it's invertible, right? Exactly. So it's the operation that dictates the fact that it's a group.
I mean, it's all together.
It's all together.
Because if we say a different set, it might not be a group anymore, or it's a different group, right? If I take real numbers, only the positive real numbers now, and I multiply them, also a group, but a different one, a very different group.
Yeah, again, the reason I said simplify is because I felt that it's just taking all these things and putting them into one. Because again, before the podcast was...
I would call it describing.
Describing.
Like, we have real numbers. What do they do? And this method of groups is sort of a little tool that helps us describe what do they like, what do they do.
So groups are not like a bunch of... So is it describing like all the things that they can do, or is it describing a specific thing? Like each group describes a specific thing that you can do. Like there's a group for, again, I don't even know examples, but I'm just thinking, are there groups for specific operations, or when you say group, you simply or when you say group, you simply mean like the set of operations that you can do?
So if I look at like all the possible operations,
right, would that be a group in itself?
Sometimes it is, and sometimes it's not at all.
That's
like a category theory level of like in the category of groups,
right?
Which things? But no, we'll not talk about that.
No,
that's
okay.
That's another step of like classifying what are the possible groups that you can put on a certain set. I guess we'll talk about that actually, because I want to tell you about finite groups.
Because we were talking about how they're analogous to matrices, or at least thinking about it. And usually a matrix is a simplification. Like, for example, you'll have a crazy linear system, and then you put it all into a matrix, and voila, the whole thing's represented with this. Just a bunch of numbers. So that's why I was thinking, a group is simplifying it because it's...
So I don't know that it's even simpler, right? Like, it's still the original linear system. We just have another representation of it.
Representation.
We have another way of looking at it. And I don't want to use the word representation because group representation means a specific thing. But it means the thing that you just mentioned, that like you can think of matrices, invertible matrices, as being a group. And that the power of representation theory is to think about a group as being a bunch of matrices. And then act on a vector space with those matrices. And that tells us things that we didn't know about the group. Number theory things, things that I'm interested in.
I mean,
but I again think that's another level up.
Before we dive into a lot of that, I know you briefly mentioned that you studied, it was that one theory that we were talking about, but you were involved with group theory in your doctorate.
Yes, Galois theory.
Galois theory. Maybe
so
we can get
in my undergrad, in
the
summer of my third year, and then in fourth year, I did research in Galois theory. And then that became a topic that I was interested in my PhD.
So group theory was the topic of your PhD, was it?
Eventually, no.
Okay, so
that one didn't quite work out.
But it started there.
But it did start there, yeah. Point. And I spent a lot of time thinking about groups, and sort of Galois groups in particular relate to polynomials and roots of polynomials.
Thank you to Brilliant for sponsoring this episode of the podcast. If you've been listening so far, then I'm sure you've been liking what you've been listening to. Then go check out Brilliant, where interestingly enough, they have an entire playlist
exactly on group theory. So why not go check them out at brilliant.org/MPP, where the first 200 listeners get a 20% off your premium subscription for Brilliant. So why not go check them out? Link is in the description below, and enjoy the episode.
So if you don't mind me asking, like, what is, because we literally last episode, we just spoke about our research, right? And we were talking about how.
I know, I listened.
So what do, thank you for that. But what do you research, or again, because I've never done a mathematical research ever really. So I just don't know what entails in, researching groups, for example. Like, are you seeing how they act on different vector spaces? Are you seeing how they act on different, examples?
Sometimes yes. I would say it's a very broad field.
Like, are you investigating what the group does, or are you investigating the group itself is kind of maybe my question. Like, what are you actually
I think
researching?
those are the same thing.
Yeah, I was gonna say.
You think so? Because I feel like, I feel like one leads to the same thing. I feel like if you are investigating the group itself, it leads to what you're doing with it. But the reason why I asked it that way is because some people can simply be investigating what the group does because there's already a good definition.
But how do you
the set of groups?
How do you investigate the group itself without asking the question, what does it do?
Okay, maybe then
Well, we did do that for a while.
Wrong, 'cause that's not
just sort of abstractly studying groups by their, like, you can define generators and say, let me go back to this example with matrices. If you're looking at 2x2 complex matrices that generate some nice group that you like SU2, then you can use these Pauli matrices.
Yeah.
And that's just 3 matrices, and then okay, any other matrix with this property is some multiple of these 3 together.
Okay.
So those are like your generators, and you can just work with the group in terms of the generators and the relations.
And so where did you come in your research come into studying groups?
So my research is not a lot in groups.
Okay.
But
so
the part that is
yeah,
in representation theory, and it is like what you're describing of, like, we don't really understand these groups, but we can look at what they do.
That's exactly, yeah.
We can see how they're represented in different vector spaces of different dimensions. And the way of doing it is sort of, okay, we'll do a bunch of algebra. If these do map onto matrices of a certain size, then what? Then what happens there? What can we say about that? And sometimes they cannot, and sometimes they can, but in a way that, like, breaks down into little prime representations, sort of irreducibles. And there's a bunch of work going on right now of, like, can you classify all of these? Can you figure out what are the certain, like, prime elements in this realm?
This sounds
the
so
answer is, like, we don't know.
specific.
Right. No, I was just gonna say this sounds very, very, like, honing in onto the one, because I feel like it can't be, like, the research going on can't be very generalized, because I feel like all the general ideas are already put through, right? Because the example that you were at least talking about with what's going on right now with groups, it's as you very well said, so specialized, right? Like, are we simply trying to understand, because we already understand the major ideas of groups, are we just trying to understand, like, the specific places?
I don't even think we understand. We don't
even understand that? Okay.
We understand a little slice.
Okay. But aren't they just something that we made up?
Yes.
Right. I mean, that's most of that.
That's everything.
We're
That's
trying to
everything.
describe
Everything.
symmetry,
Right.
right? We're trying to say, what does it mean? How can you tell when something's symmetric? And to do that, we make up a bunch of stuff, different structures that we can put on it and ways that we can analyze those structures.
So,
That's fascinating.
where did group theory start? Do you know? Like, what were the first
I
kind
have
of?
some recollections. I mean, it's also kind of hard to say because sort of foundations of math changed a lot in the 1800s when groups were being recognized as something, and they sort of came up at the same time as algebraic structures. So probably things like matrices are probably older than groups. But then when people figured out, You can use matrices to describe other stuff. You can use groups. Groups used to just live in this world of permutations. Then, like, the way to talk about a group was to say that it's some collection of permutations of some objects. And that didn't let us do, like, infinite stuff. So, mid-1800s, late 1800s.
Because, I'm just guessing that the study of groups has gone from something rather simple and then blossomed into very complicated ideas nowadays, I'm guessing. And so I guess my question is, if we were to go back to when, like, groups were just being thought of, like, what were the foundational ideas that were being brought up at its inception?
Sure. So a lot of it starts with finite groups. That is, can you figure out what are the possible group structures you can put on a finite set? Like if I say, there's a group and it has 5 elements in it. Can you write down the multiplication table for these 5 elements? And it's going to look like a little Sudoku. And because everything has an inverse, so there should be like 1 of each element in every row and 1 of each in every column. But this composition has its own little structure, which is if you do 3 things, it shouldn't matter which 2 you do first.
Mm-hmm.
So if I do AB and then compose that with C, that should be the same as if I did A with BC. Doing like BC first and then put A, put it on the left, put the same order. That puts a big restriction on stuff.
A restriction?
Yes.
Right.
So like not every Sudoku that you fill out will have that, follow that rule.
This is not every
But doesn't that make...
right?
I'm sorry?
This is not every group, though.
Every group has this property, yes. The composition must be associative, we would say. It doesn't have to work like symmetric. It doesn't have to work commutative, exactly. So like you're thinking of like matrix groups. If you take invertible matrices and use multiplication, if somebody writes like A times B times C, you don't have to ask them which one they did first. Those are the same. But if you do AB, that might be different than BA.
In the case of this multiplication table, it is commutative, though, because you're just dealing with multiplying numbers.
For 5? Oh,
Yeah.
I'm saying like the operation can be whatever,
Right.
right? Like you have 5 things. They might be
Okay.
5 letters.
Okay. Yeah.
They don't necessarily do like addition, multiplication like numbers do. Now, in the case of 5, yeah, try it out. Do it. There is only one. With 4, there's 2 different ways you could do it. And with 6, there's some non-commutative ways you can do it.
Wait, sorry, do what?
Fill out a table.
Oh, okay.
How about this? It'll go like we like to use E as the sort of 0 as the identity element, but you would have like E and then A and then B and then C, and I'm going to multiply those things by E and then A and then B and then C. And E times anything will just be itself.
Oh, so you have to define these rules.
And now I have to define like what's going to go in those extra little spots down there. And what I need is Sudoku rules. I need 1 of everything in every row and every column.
Right.
So you can start choosing, like, what do you want to go here?
Does it have to be one of E,
It can't
A,
be an
B,
A,
C?
but yes, it has to be one
Okay.
of these things. We're not going to go outside of the group.
But I could say any letter.
Well, don't pick A,
Why not?
because there's already an A in that row.
You have to pick B
Oh.
or some other thing.
Yeah.
Wait, so
Okay.
if you do B,
Now I'm just
you
confused.
do B, C, E, you can do another E in there.
What do you want? You want E here?
Well, I was just thinking B, C, E, but yeah, I mean, E, B, C would also work. No. E, B, C doesn't work. It's B, C, E, right? Yeah. B,
Just
C,
for the audio listeners out there.
Right. No, I think
where-
he was showing. Oh,
I got the
okay.
first row is going to be E, A, B, C, and Ray wants the second row to be that shifted.
Right.
So it goes A, B, C, E.
My whole idea is just to keep shifting it.
Okay.
Won't that work? Oh, wait, am I
So
right?
yeah,
Won't that work?
just for the audio listeners, we're filling out a table,
A 4x4.
a 4x4
grid.
grid.
Like a multiplication table.
Yeah, like a multiplication table, but they're letters instead of numbers, and we get to decide what goes in each spot.
So
Just
Ray
basically,
says
sorry.
A times A should give us B. And then he wants B times A to be C. And we're just going to
Yep.
cycle again
keep
so that
cycling.
B times C is A. Okay, interesting. And then our last one is
Just
going to be
cycle again.
decided because we
Cycle.
have to put 1 in every row and every column.
So,
Pretty time.
Okay.
so we get to
That's a group.
decide.
Sudoku.
We get to decide what the action of each element on
On the
another
other
element
elements.
gets.
Yes.
Okay.
And the reason you said there are only 2 is because, the moment you switch C, that doesn't work anymore. Or you can do it for C again, but then you can't do it all the way
Yeah,
again.
try to
right?
make up these tables.
Right, that's what I'm saying.
There's
you can't do it
2
3.
different problems that
Okay.
can show up. One is you have to remember things are associative, which can be hard to read in a table. That if I do like, okay, A times B times C has to give me the same thing as A times B times C. And A times B is something in this table, and B times C is something else in this table.
Right.
And then I have to do another comparison to make sure.
Oh, right.
So
we
why
actually check it that way.
why are we guaranteed associability when we just make up
We're
this
not,
table? Oh, we're not. So how can you say that this is a group?
Because that's not associated.
because I recognize it.
Oh,
it is.
This is my
okay.
friend C4.
Okay.
Wait, really?
This is the cyclic group
Oh,
of 4 elements.
No way, that's cool. We just.
It's just like doing mod 4 addition. 1, 2, 3, 0, 1, 2, 3.
Oh,
And if you want, you can switch them all out. Make E0, make A1. This says what? 1 plus 1 equals 2. 1 plus 2 equals 3. 1 plus 3 equals 0
Oh,
again.
work.
Hmm.
Oh, they actually work. Oh, damn. That's
3
cool.
plus 3 gives me 2. Mod
Yeah.
4.
Very interesting.
yeah.
Wow.
Wow.
Cyclic
Cool.
group.
There
just
you go.
invented on the pod. No, sorry.
Discovered.
Discovered. We discovered.
Exactly. That's
Um,
pretty
And so
sick.
what is
And your
the
plan, your idea that you
Yeah.
can just keep shifting
Yeah.
is true. So for every number that you want, there's always that cyclic group.
Oh.
And you can think about it as the
That's
symmetries of sort of like pick points on a circle that are equally spaced. Or if you want, here a square, but I'm not going to turn to the other side. I'm just going to do rotations, 1, 2, 3,
Right.
4. And as soon as I've gone all the way 4 times around, I'm back to where I started.
Right. So if you imagine
This is this.
if you imagine a square and you just label each one of the corners with one of these elements, here we said E, A, B, C, but it could be 0, 1, 2, 3. And then if you were to say, okay, let's start as 0 and we add 3, it's like rotating it 3 times. And then what element do you get there? Well, you would get a 3. But if you were to add another 3, you rotate it 3 times, you would end up at, right, 0, 1, 2. So that's exactly what we were doing on the board there. It's the same as just rotating a square with those elements on the corners.
Yeah, that's sick.
Yeah.
Now, there's another group. And I think Parker wanted to do a thing where you can put an E right at the start. I'm just going to redraw this table again, and I put the same first line. But now I want A times A to equal E. And then I can fill in the rest. Of course,
Yeah, you can keep.
I can't put a B and a C here. Fine. I'm going to do those in reverse. And then down here, similar problem.
Oh wait,
Okay.
you're not doing cyclic anymore. You're just. Okay.
Mm. Right, so here the condition is that A times A equals E. Then what?
Then what?
Right?
So now, can we fill this out? Can we fill in the remaining 2 by 2 part? I put in everything below E and A and across from E and A because those were determined. I have to get one of every letter in every row and every column. Sudoku rule. And then what do I do in this last part?
You just have A's and E's left.
I have A's and E's. So we can make B times B equal A, and then that will decide everything else. Or we can make B times B equal to E,
Yeah.
and that will also decide everything else.
Like the E's could just go on the diagonal.
The E's can go on the diagonal.
But is that? I'm sure you're thinking of this, but I'm not even thinking about the associativity when we're doing this.
The associativity is another thing to check.
Yeah.
You
I'm
cannot.
not even
I
thinking
cannot
about
look at it and
I'm
think
not even-
about it.
Okay, 'cause
Right.
I have to go. This is
Yeah.
what I'm doing last night. I was like, is 4x4 a small enough example that works?
Yeah.
Like, okay, I think it is.
Yeah,
But I
4x4
have to
is
check.
good.
Like associativity is a problem. But here, okay, this is going to highlight two different issues we have. One, if you do put those e's there, this actually is a different group. Now we have B times B and C times C and A times A. They all give us the identity.
So that's not invertible.
They're each invertible.
Because if you transform to E, how do you know which element to go back on? Right.
I mean, whichever one you used.
But if I were to start with E
Okay.
and apply the inverse
Of what?
of this operate, like you're given E, A, B, C,
Mm-hmm.
and this rule for transforming the elements. And I say, okay, I give you E, and I say, what is the inverse of the transformation?
Of E?
No, E is what you're applying it to. Does this not make sense?
I totally understand what you're saying. He's just saying because A by A, B by B, C times C.
Oh,
they're
they
all
both
equal
bring
to
me
the same
back.
thing.
Yeah,
So
they-
when
You don't know
when
where we
back
came
transform-
from.
Yeah, you don't know which way you came
That's
from.
true. You don't know where we came from.
So it's
So-
not invertible.
No, it's invertible.
Oh.
I mean, if you know what operation you did, you can undo it.
Okay, yeah.
Right?
If you know
if
what
I
you
have
did in
A
the
and I
first
multiply
place.
by A, I can multiply by A again.
So it's not surjective.
It's also surjective.
Okay. Oh no, it's not.
You
sorry.
can tell this rule about like there's always one of everything in every row in
No,
every
it's not.
column.
Oh right.
It
Okay. Yeah, that
means
makes sense.
There must be something that gets sent to E, and that's going to be the
Oh,
inverse.
I was thinking about this all wrong the entire time because every letter is a different function, right? So
But also is a thing.
yeah,
in
it is
space.
also a
Yeah,
thing,
that's
right?
the
I was
confusing
I was
part.
thinking of the whole table as one function, but it's
No, you
It's-
Try to think of it
fine,
like
right,
when you take the
yeah.
real numbers except for 0 and you multiply by 2.
yeah.
You again get all the real numbers. And if somebody didn't tell you that they multiply by 2, you go, well, there's no way I can undo. I can't tell what we started with or what you multiplied by. But if they tell you what they multiplied by, you can undo it.
Yeah, you would know. Okay. That makes sense.
That is actually, yeah, that's interesting. And you mentioned.
So let me not put in
that's the
E's
typical
here.
4x4, Right.
Let me do the alternate version, which is what if I put
Right.
an A there?
Okay.
So now there are A's on the
Now this is
diagonal.
another.
There's A's on 2 of the diagonals. So
Two
I made
of the
B times
diagonals.
B equal to A, and I made C times C equal to A.
While both the identity and A times A are both E.
Right.
Like I don't even know what to think. Am I really?
Yeah, I
gonna
don't
do this
know.
in my
I don't
head?
know what to think right
Am
now.
I gonna do the
Yeah. Do
associate-
you recognize this group?
No.
think?
Okay.
That was really fast.
Okay.
Well, you can say no right away. Like,
You didn't even think.
you ever seen this guy before? Nah, never. Never seen it in my life.
Okay. By the
Okay.
way, for the listeners, we're
just staring at
a piece of
this.
paper.
We're just staring at a
Just
piece of
staring
paper right now.
at the.
Do
Trying
you
to
recognize the guy in the bottom right? We know who the big one is. That's C4.
I want to ask a question about that after because I don't really know what that is, and I know he mentions it a lot, like C3, C4, and whatnot.
Oh, C is for cyclic, and we're saying like it's like points on a circle, and you can rotate them.
Oh, that's far easier than what I was.
So
I
if you
thought
want to
it was
represent like C4 is really the numbers 1, I, minus 1, minus
minus
I.
Yeah, yeah.
And if you multiply
yeah.
those together, you can think of E, A, B, and C being 1, I, minus 1, minus I.
So all of this is complex. Is that true?
Not
Not
necessarily.
necessarily. Not necessarily.
You can just map this onto that problem,
Yeah.
right? Because just by given the elements and the operations of each other, what they give, it's the same thing if you were to use those complex numbers, right? So it's a way
So
to look
the
at
complex ones can describe the abelian versions, where
Right.
the multiplication is commutative.
it.
But if we don't have a commutative multiplication, like with matrices, then we can't say that they're like complex numbers.
Sorry, we still haven't figured out that group. I don't think I have an answer, to be honest.
Well, you do. This is C4 again.
Oh.
These are the same.
Oh, wait.
Wait, why?
So
But
instead of here, imagine this number A as being 2.
You just replaced.
I moved them around.
You
Right,
just.
so now 2 plus 2 gives me 0, mod 4. 2 plus 1 gives me 3. Did I do that right? 1 plus 1 gives me 2. 3 plus 3 gives me 2.
Yeah.
Oh, you just literally.
Yes.
Just rearranged it.
So you should not be upset about this. This is a fundamental problem that we have, which is recognizing a group.
Does this
How
have
do we
to do,
know when
does it-
two groups are the same?
Does it have to do with the permutations that you were talking about earlier?
Certainly.
How like the permutations of elements also is part of a group, or I don't know the wording, but
Well, so if I give a representation of a group, like we took these E, A, B, C, and we said you can think of them like 0, 1, 2, 3, and add them mod 4, that's one way to describe that group. But if
Yeah.
someone gives you a different description, how do you know if it's the same group or a different group? And that's a fundamentally challenging problem.
oh, there's no answer.
There's not a good we don't have good ways. So what we try to do is figure out different properties of groups, how we can compare them with each other. We do have a really good way if the groups are abelian, but if they're not, it's a struggle. This is called the group isomorphism problem, and it's just a famous hard problem.
There's actually a question that I have listed here on explaining the first isomorphism theorem,
Okay.
which is apparently
That's an important
you mentioned
theorem.
the word, so here's my question: does it have anything to do with it, or is it like a very important theorem that might
So-
describe?
Isomorphism, a morphism is like a map or a function, and iso means if they're the same or not. So iso means same,
So auto is on itself.
Auto is on itself.
and iso is
the same.
the same. Okay. So a group is automorphic. Is that correct language? No,
I would not
A
say
group is
this.
isomorphic.
That does mean something, but that's not what you want it to mean.
Okay. Oh damn. That's more
You would
more
say like
complicated.
one group is isomorphic to another group.
Oh right. No, obviously the same. Yeah,
Sort
yeah.
of like things being equal.
No, obviously.
You got to describe
right.
them both.
But a group is automorphic. Makes sense. Or no?
We would also not.
No,
that
not really.
is a meaningful term, but it's not the
on
thing that you
itself,
want it to
no.
mean.
Okay, but I think I understand a little bit about the word. So yeah, if you want to continue on what the theorem is, or if it's important at all in relevance to.
Yeah, so this
Yeah.
first isomorphism theorem, I don't know. How much do you want to know?
Probably
you want-
surface level.
much-
It
do you wanna
sort
tell
of
us?
tells us. Okay, how about this? If you think about them like vector spaces, this is a good way I like to do this.
Okay.
Is you can map one vector space to another vector space with a matrix. And then if you know things about that matrix, like what's the kernel of the matrix, which vectors does it send to 0, and if you know some stuff like what's the image of the matrix, then you can sort of reconstruct what this original space looked like. Because there's a certain amount of things that there's a subspace that all gets sent to 0. There's a subspace that gets sent to something that looks like itself. That's the image. And together, those two pieces fit together and make your original space.
This is sounding like rank nullity.
It's exactly rank nullity.
Yeah.
So the first isomorphism theorem is rank nullity for groups. It's exactly the same thing.
Wow.
So what is the equivalent of rank, the rank of a group?
It
Or the
would be
nullity.
something like the image of the. So we need a function between groups, I suppose, right? We need a
Right.
group morphism. So you have one group
Okay.
and another group, and we have some way of sending things from one to another.
So the elements.
In this example, like with two C4s, I
Mm-hmm.
can say send B to 1 and send A to 2 and send C to 3. That's an isomorphism with the set Z mod 4.
And we can also,
Sorry, that's a group morphism.
would we also be allowed to transform the operation in this?
Yes.
Okay, so you can send, let's say, addition to multiplication on
You know a
different.
very famous thing that
different
sends
elements.
addition to multiplication, and it's the exponential.
Yeah.
And the exponential is a group homomorphism between the real numbers the positive real numbers with multiplication, and the regular, all the real numbers with addition. Then if you want to add together real numbers, you can, instead of doing that, take an exponential and then multiply some positive real numbers.
Mm-hmm.
Or if you needed to multiply positive real numbers, instead of doing that, you can take a log and move down into the adding group.
Interesting.
I never thought of those as different groups, though. Like, I guess going into this space.
Yeah,
maybe
if one has
trying to
addition and one
think.
has multiplication, the operations
Right.
are different.
No,
But
but
even-
you described like the log space as a group in essence, or did I misunderstand that? But I think you were trying to say like the
Yeah.
addition group.
I'm thinking of
Right,
that as
so
the addition. Yeah.
This is a very interesting way to think about. Because again, I mean,
That's
not
where I
that-
add
yeah,
stuff, right? In log space. I want to add things. And in that exponential, I want to multiply things.
Mm-hmm.
That's pretty fascinating. So you were mentioning finite groups as well, and infinite groups and possibilities of them,
Sure.
and how a 2x2 is also an infinite group, for example. So,
So if we talk about if we take all the invertible 2x2 matrices,
Right.
that's a group because we can multiply matrices and everything has an inverse. But it's an infinite group. There's infinitely many things in it, right? Different matrices.
right.
Whereas these finite groups, we just have some certain number, and we want to know what's the multiplications, or what's the operation we can put on this set to make it into a group.
So my understanding is right. These are all finite groups.
Yes, sorry,
Right,
C4
right,
is
right,
finite.
right. Okay.
And you gave your example of an infinite family of finite groups. If you just make this Sudoku and you keep shifting by one, that always makes a group. It always makes this cyclic group. So you get one for
Well,
every
like
number.
Infinite.
But
Oh.
you get one for every number, right? Any Cn that you want.
Oh.
And sometimes that's the only possible one you can get.
I want to bring this back to the theorem that we almost finished talking about.
No, we finished. It. Oh.
About rectangle.
Right, because
Did I?
so we were talking about how, what does it mean for a group morphism to have a rank or to have a kernel? What does that even mean? What does it mean
so
to
the kernel
send?
is easier to describe. It's
Okay.
just like in the matrix case, it's all the things that get sent to the zero.
Yeah.
And the zero in a group case is whatever the identity is. There's an element that doesn't do anything. And we know it's there because everything has an inverse. So if you do something and then it's inverse, you get something in the group. That's the identity.
Okay.
So the kernel is asking what things got sent to the zero,
Right.
the zero in the space.
So
And then for rank, we don't exactly have a numerical
Yeah.
thing. What we do instead is just take the original group and quotient and mod out by all of the things that got sent to the identity. So we would say, these two elements are equivalent because I sent something to the identity.
mm-hmm.
In the C4 case, if you want, you can think of them, send all the even numbers to 0 and send all the odd numbers to 1. And that's a group homomorphism from C4 to C2.
Oh, yes.
And it tells you something about C4, that secretly it was really two copies of C2 together.
Yes, this actually connects the dots on something my prof wrote on the board. He said SU2 squiggly line Z2 equals SO3 is what he said.
Sure, yes.
And so basically, I think what this means is you have SU2, which I guess we'll describe in a sec, but I just want to get this out. You have SU2, and if you divide out by Z2, then you get SO3, basically mod a negative sign, I think is what I'm trying to say.
Well, those are in that Z2, right? But, okay, sure, yes. So
Yes.
SO3 is saying what are all of the different orthogonal 3x3 matrices. So matrix transformations that preserve lengths, and I guess angles. And then the S part is saying just take the determinant 1 matrices. You're not allowed to go into like mirror world. Everything is turned inside out. Just stay in the regular space where we're moving around in. So that SO3 is describing all the different ways you can move around in space, just sort of like rotations and reflection, but not a single reflection.
All right.
And then SU2 is this, SU3 you want to describe?
SU2.
SU2
SU2 and Z.
is this Lie algebra that is sort of describing tangents in this world, or if there's an exponential. I don't know how much you want to get into Lie algebra.
No, it's okay. No, I just...
We actually had Mihai talk about this.
Yeah, I do.
And Lie is another hard name, math name, because he's Swedish Norwegian at a time when those are the same country. And Lie is spelled Lie. If you want to look up Sophus Lie.
So that's why it's pronounced that way. That's interesting, actually. That's pretty sad for his name, though, because now he's not known like he was known, you know. Now, when you say lie, you're like, who's lie?
Well, we don't say lie.
You don't
That's
say
why we
lie,
say
you
Lie.
say Lee.
Oh, you actually...
we do try to make them
Let's just follow
known the
him.
way he was
Let's
known.
just follow him from that. That's okay.
Yeah.
But yeah, so the way to think about like first isomorphism theorem in groups, I think, is like rank nullity. There's not necessarily a
sense.
thing that is like the rank, but more like the image, or like what's the equivalent, what stuff did not get sent to something like 0.
So you mentioned something briefly about SU2 divided by SU3 gives you SO or something like that. And that just got me thinking, no, it has nothing to do with that. It just got me thinking, like, can you do I mean, I'm sure you can, but just the question, you can do operations between groups, can you? Is that meaningful?
We have some great ways
when
to
you
combine
divide-
groups together.
Right. So what does it mean when you divide? Because again, my very surface level understanding of groups, as you mentioned, is like things that you do to objects. So when you like multiply or divide versus add and subtract, can you add and subtract groups? Like, what are the and
how
does it
can
mean
you
when do
combine
that?
groups?
Exactly. How
There's
can you combine groups?
a real nice, simple way is like direct product of groups. Where
Okay.
you can sort of think of, instead of just adding like 0, 1, 2, 3, what if you had pairs? What if you had all of the 16 different combinations of 0s and 1s and 2s and 3s as two-dimensional vectors? Then you can do a C4 on the first one, you can do a C4 on the second one, and you can have a whole group that's like C4 cross C4. You get a bunch of different ways of moving these 16 things to each other. So you can build up groups like that. There's other fancier ways of doing products, like a wreath product.
But what does a product mean exactly? Because again, like I think I think I get the math, but my question is like, what does it mean when you do? Like maybe you can give an example of like simple groups, like you were talking about rotating squares, for example. Like, what do you mean when you have a group of something multiplied by a group of something else?
Oh, it'd be
maybe
like
you
if I
can
have
give
2 squares.
Oh, okay.
Like I could turn
I thought
one
it's the same
square
square. Wait.
independently. I can turn
Oh
this other
yeah,
square.
that actually
I was
totally
thinking
makes
it's
sense.
the same square. You're saying they're
No, right.
Oh.
That makes well. He said you take C4 and you cross it with C4. You know.
Right.
Now, if you just cross 2 different objects together, you rotate one of them, the pair still looks the same. You know, or you can rotate both, but the pair still looks the same. Interesting.
So like a group of, hold up, I think I mentioned this before and you said that's wrong, so but just maybe correct me again, but like a group, so when you multiply 2 groups, that can be a new group?
Yes.
Oh.
And it can describe different ways of combining the objects. So the one way of like, okay, you take a square, you take another square, and you just independently turn them. That's
Right,
a perfectly good way
Yeah.
to make a group. What if I took a square, I glued it on the back of the other square? I can make a new group
Ooh.
that describes this kind of a product, where I've taken like a C2 that is like a flip, and I stuck it onto a C4, but in a way that's not like, if I can't do them independently. Maybe I can get this to show because it'll face upright, but if I turn it counterclockwise and then flip it. Maybe I'm going to flip first. Let me flip, turn it counterclockwise, flip it back. It ends up words facing this way.
Not the same way, right?
But if I just do, how do I get that from here? I have to turn it the opposite direction than the way that I originally turned.
So is this an
Oh,
example?
I see what you just did there. Sorry.
This would also demonstrate the fact that it's not commutative, right? Because
Yes.
the order in which you flip and rotate does matter.
Yes.
Yeah.
So here's an example that is called a dihedral group. It's dihedral because there's two sides. Hedron is a face. So if we take something that has two faces, we can figure out the symmetries of each of them and then glue those groups together along a way that maps from like a flip.
Right, but we don't need commutivity.
No.
Yeah, we don't.
We
need
don't
it.
ask
We just
for
need
commutativity.
associativity.
Yeah.
Okay.
And
So I
now
was
this
gonna
is a different way of making a product. It's not this direct product. It's a kind of fancier. The new group doesn't just act independently, it does something to the original group also. In this case, it turns it backwards.
Would you be allowed to glue, let's say, an octagon on the back of a square?
Sure.
But I guess that would kind
I'm
of
thinking
reduce.
this works out because 4 divides 8.
Yeah, that's what I was thinking.
If we took two groups and they have like co-prime number of elements in them, like if you took a pentagon and a square and you ask for symmetries, there's not going to be a symmetry that keeps them both looking like they were.
No.
But you can just say, let me take the whole collection. Let me take all 20 different turns of 5 and 4. Yeah, that's a group. They're just not going to have the cohesive. They won't have any wreath product. There won't be.
So it's
Although
not.
I don't want to say that. Let me not say that. There's definitely going to be numbers where they do exist like that, and probably 20 might be one of them. Okay. There's a big problem with finite groups, and it's that we don't know what they are.
Wait, the finite is the problem. I thought the infinite.
The
was
whole
problem.
thing
Oh,
are open problems.
okay. Jeez.
Let me give you some stats.
Sure.
So I told you, there's at least one group of every size
Right.
from doing this cyclic thing.
Oh yeah, of course.
If that size is prime, that's the only possible group.
Oh.
That is so fascinating. Really.
So
So-
the primes are very special.
because you mentioned C3 only has one.
C3 only has one.
So every.
C5 is the only one. C7
Fascinating.
is the only one.
So let's say you discover
What?
a group. Would it be the number of elements?
We usually describe the number of elements. That's the size of the group.
So let's say you discover a group of size 11, and then a different way you discover another one that's size 11. They automatically
They're
have to
definitely
be
the same group.
Okay.
Now, we don't always know the isomorphism,
Right.
but and oftentimes like there are multiple ways to go from like describing them. But yes, those are definitely the same group. But now let me go up a little bit. Let's say like for some powers, if I multiply numbers together, I suddenly have lots more combinations of what I can do. So these sort of composite sizes get way more groups in them.
Is it kind of a function of the number of factors, the number of prime factors?
The number of factors makes a big difference. We get a lot of them when the primes are repeated. So I think the current, what's cutting edge? So 1,024, that's 2 to the 10. Something like 15 years ago, we figured out how many groups there are with 2 to the 10 elements.
How can you be sure that the number that you found encompasses every single group?
That's a good question.
Yeah.
Some people also had found out the number earlier, but I was incorrect. We do it very carefully. But here's this amazing thing is that there's so many more of size 1,024 than of any other size nearby. So if you look at all of the possible groups up to size 2000, if you pick one at random, something like 99.9% of the time, it's got size 1024.
Wow.
They're almost all there.
Wow.
Wait, sorry, what?
Lay out all of the groups from size 1 to
There's so
2000.
many, is what you're saying.
Yeah.
There's so many at that one place.
Yeah.
And what? Sorry, could you explain why that is? I know you mentioned the 2 to the 10.
Well,
but
2 to the 10, there's just a lot of different ways that you can fill out this table.
How do we even figure
the
that
things
out?
of twos? That's another very good question. Here's another follow-up. If you want to try to figure out, we don't know the number for 2 to the 11. We don't know how many groups there are with 2,048 elements.
It's definitely way bigger.
It's definitely way
Then-
bigger.
Wait, but
We have some lower bounds. We know the exact size of a certain big, useful set of them, but we don't know. There's like these extra ones, and we don't know how to count them.
so now I'm seriously curious on how we got the 10 to the 24. I mean, 2 to the 10, because I mean, I would assume that there's like some sort of formula or something pointing you towards count.
Wouldn't that
Like,
be
how
nice?
do you do the 2 to the 10? You don't count them.
If you're on, you can look up the Online Encyclopedia of Integer Sequences, OEIS, and it gives a list of a whole bunch of different things that involve integers. The very first sequence in the OEIS is how many groups are there of a given size,
Wow.
and we do not have a function for it.
Wow.
I can tell you what the answer for every prime. So one.
But then how did they? I still don't get how they figured.
There's a
out
lot
the
of
2 to the
stuff.
10. Maybe. Oh my, that's just confusing.
It's a lot of structure, right? It's a lot of analyzing what can possibly go in these spots.
Is there a simple reason why the prime numbers only have one group? Or is it complicated?
That's a good question. I guess. So we know they have at least one,
At least one.
because you can think about, the regular polygon. You can definitely rotate. The cyclic
Right.
group is always there.
Right.
So how come there's not any other one? That's a good question. I guess I would look at, okay, there's some element. What happens if I compose it with itself over and over again? Eventually, I know I land back at the identity.
How do you know that?
Either because I know there's an identity somewhere in my row, or if I only have finitely many elements that I can ever hit. So if I just keep track of
Right.
them, like if I go, okay, it goes A and then B and then C and then R and then T, and then if I ever get a repeat, then I
Right.
know exactly that many A's in between the repeats was the identity. Right, so like if the second and the fifth thing are both the same, then I know it only took me 4 steps. 2 to 3,
Right.
3 to 4, 4 to 5. Only took me 3 steps to get to doing nothing.
Mm-hmm.
So it's finite. There has to be a repeat. That number of steps got me the identity. And then we do a little number theory, and we get something like Lagrange's theorem that says this would be called the order of the element, the number of times I have to multiply by itself to get to the identity, that has to divide the size of the group. So then I know.
So if it's prime,
It
then
had to
there's
have been
only
more prime.
there's only one option.
Yes. And then I can describe the whole group as just being some number of multiples of this one thing, which is exactly the cyclic group. So was that easy?
That was
proof?
easy enough, yeah.
Okay.
Yeah.
Oh,
Wow. So
But yeah, the non-primes, the composites are fascinating, and we still do not understand them.
I'm still trying to figure out, man. My head's. I'm still trying to figure out the 2 to the 10 thing.
It's mind-blowing, right?
Or even
There's just so many more of that size.
Or let me pose. What about 2 to the 5? Or like 2
yes,
to the 7?
so smaller ones. So Every
Right.
new one is like a record breaker in terms of the number of groups of that size.
Okay.
So I told you what there's one group of size 5 and one of size 7, of course. For 6, I guess there's 2 groups of size 6.
But 8 is
And
gonna
for
be, like,
8,
crazy.
there's going to be, I think there's only 5 of them.
Okay. Well, way
Is that
more
right?
than the ones before.
Quaternions, there's 2 non-abelian ones, and then there's the 3 nice ones. Yeah, 5. I think there's 5.
Okay. So there's 5 for the.
And then there aren't 5 of another group for a while.
Is there really no pattern? Pattern to show that? Because
I tell you, it's tough stuff.
I mean, that's like
As soon as you
asking
get
for
to
the primes.
PQ,
I know,
Basically,
but
it's
I
hard.
guess it's like, I guess
Is
it's
there
similar.
is there a pattern for the primes?
No, because I'm just saying if 2 to the if 2 to the. Why 2 to the? What about 3 to the?
Yes.
What about 4
So
to the?
3 and
Or
4
I guess.
will also have a lot of
So
groups.
3 like powers of 3.
So like 3 to the 4, there's more groups of size 81 than there are of 2 to the 4, 16.
Wait a second. Oh, so
It's just that it's bigger, so we don't get to it as you see
Right.
the test.
so 3 to the so
3 to the 10 probably beats 2 to the
that,
10.
I was just gonna ask that exactly.
We have no
okay,
idea.
exactly.
But it's just way bigger.
Exactly. No,
But
exactly.
also, you said 4 to the power, but
No,
that's
I know,
also
I-
2 to
that's why I
the.
corrected myself. That's why I
Yeah.
corrected myself. But so is there any property about? No, probably not. Because there's nothing that we get primes. No, I was just thinking about if prime, like to the power of anything gives. I mean, I'm just thinking
Sure.
about any kind
So
of power.
prime squareds have a really nice structure.
Oh, so there is something. Okay, that's interesting.
If you know that your group has an order that's prime squared, then you can say some things about it. It's very restricted.
Really?
Mm.
And prime cubed is a little bit restricted, but it gets kind of messy already. And then
Because-
bigger powers is like we don't have sort of structure theorems about what they have to look like. And they can have really strange, interesting structures.
So then it really must bog down to the factors or like the number of factors in essence.
And sort of how you can mash them together. Kind of
So-
like I can have a group of order 8. I don't need to spin it 8 times. I might have like 4 spins and a flip. Or I might have 4 spins and then separately a flip that doesn't affect the 4 spins.
But then
And I might have
sorry.
something else that is more like complex number multiplication, matrix multiplication.
The reason I asked that specifically is because like 3, for example.
In fact, you
Wait,
have this
would
group,
it-
right? You have like IJK and the -1 and
For what?
the quaternions.
Oh, I'm not very familiar. I know what
Okay.
they are, but
Because 3, because the whole point of 2 is that it like 2 to the power of something. Correct me if I'm wrong. Like 2 to the power of 5 would have more factors than 3 to the power of 5, for example, right?
Factors as a number, they'll have the same number of factors. Exactly the same.
yeah, because
6.
wait,
Wait,
what?
give it the example.
One second.
What?
How?
2 to the 5 has 6 factors, right?
No, well, I mean,
Yeah.
I just spitballed a number, but I'm just thinking like
I
2
took
to
the
the 5 and 3 to the 5 have the same number of factors.
Yeah, because it's 2 times 2 times 2
Okay,
times 2.
no, again, I'm not thinking, mate, I'm trying to generalize it, like 2 to the n versus 3 to the n. I'm trying to generalize it.
Still, they would have n factors.
n plus 1.
Wait, what? If you're multiplying it n times,
Uh-huh.
you have n factors? Or n plus 1?
Maybe
you
we mean
said?
different things by factors. I'm
No,
talking
wait,
about like
I know what you're
divisors.
talking about. I'm talking about factors, like 6
Numbers
has
that
factors
divide it,
2,
yes.
3, and 6.
Yes.
1, 2, 3, and 6. Like
So
factors.
2 to the 5 and
Oh,
3 to the
yeah,
5
yeah.
I'm saying.
have
Okay.
the same
That's
number
what
of
I'm saying.
factors.
Okay.
So, but that, I don't get that. Like,
Yeah, I don't know.
Like how is 2 to the n and 3 to the n have same number of factors?
Oh, this is back to like our number theory episode,
Oh,
right?
right. I guess
If
it
you
is a
want to
little bit.
take,
I guess
how do
it
you
is a
write down a
little bit.
factor of 2 to the n? Well, it's 2 to some power, and the power has to be between 0 and n.
Right.
So there's n plus 1 of them.
Oh. Yeah. That makes sense.
What? Wait a second.
Well, if you're counting the factors of 2 to the n, you have 1, which is 2 to the 0, 2, 4, and then all the way up to 2 to
Oh,
the
because
n.
right, we're counting the numbers themselves. Right. No, obviously in that case, I feel like because you're counting, but even 3, for example. Wait, 3, for example.
But in terms of number of groups, 2 to the n and 3 to the n have a different number of groups for n bigger than, I think 4 even is small enough. I think 16 and 81 is distinct.
No, because that's really why I was asking. I'm like, is there something special with 2 to the 10, or like 2 to the 5 versus 5 to the 5? Like, would 5 to the 5 have more groups?
I think yes.
But they won't have
But
the same amount
look this
of
up. Group props wiki. They have some information.
Would they
The
have?
things that are known, they have all the stuff that we know. I think 5 to the 5 might be like beyond our realm of comprehension.
Yeah, that's wait.
Because it takes also a lot of computational
Yeah.
power to like search through the possible Sudokus and see which ones are associative.
Yeah. This actually reminds me very lightly on something I'm doing right now in combinatorics, where it's like the R number. Do you know, for like a graph of size n, it has like n points.
Mm-hmm.
You want to know the amount of ways that you can make a triangle between 3 points.
Oh, okay. Counting triangles in a graph.
Yeah, counting triangles.
Sure.
And something like the R number for a graph of size 5 is doable, but no one knows the answer.
Oh, like Ramsey?
Yeah, Ramsey.
Oh,
yeah,
okay,
yeah. But if it's like R6, then it's like forget about it because it's way too big of a number for
So-
somebody to find out.
Even, 5 is hard.
Yeah. Yeah.
5 we don't know.
I think
So this is a problem of like, you have some graph and you color in the edges.
yeah.
And we want to know, can you find a collection of points, like 5 of them that are all connected to each other with the same color?
Sorry, quickly. Edges of a graph. So I don't know if I'm personally
Just
familiar with that.
Imagine points and the
Yeah.
points are connected.
No, but you
So
mentioned
an
the word
edge,
edges. Which
yeah,
is
an edge is what connects 2 points together.
Oh.
Yeah.
Okay. That's just okay. I understand.
So if
Yeah.
you take like 5 points and you make a little star shape and you make a little pentagon around them, then you've made all the possible connections of those 5 things.
Mm-hmm.
And so there'll be 5 times 4 divided by 2, 10 edges. Or 5 choose 2. And then in that case, it's possible that you can color them. You can color the whole pentagon blue, you can color the whole star red, and you never get a triangle.
Mm-hmm.
But if you have 6 points and you color the edges, no matter how you color them, there's always a triangle in the same color.
Mm-hmm.
Whoa.
So essentially,
That's sick.
the question is, how many
Pretty cool.
for a given number of points, what is the number of edges in which you cannot?
Like, how big of
Make
a
that
graph
shape,
do you
yeah.
need to guarantee that you can find
Yeah,
one of
exactly.
them?
That was way better. Way
That's-
better.
I've said it a bunch of
Yeah,
times.
yeah.
I understood
You
what
said it
just
way
said right
better.
there. How big of a graph do you need?
So,
To
like, the next thing after
guarantee-
triangle would be like, okay, what if you had 4 points all connected to each other? So it makes like a little square with an X through it.
Yeah.
Mm-hmm.
How many do you need to guarantee that you get that? And I think you need 18, 17 or 18. I think 17. You can take 17 points. You can draw all the possible 17 times 16 divided by 2 connections between them. You can make them 2 different colors, and you don't get this square with an X in it.
Mm-hmm.
But once you get to 18, you're guaranteed to have one.
Mm.
So this is some very hard combinatorics problem as soon as we get up to 5 and 6.
Yeah, 5 and 6. 5.
The numbers are big.
It was. I think it was the Ramsey number.
Yes, these are Ramsey numbers.
I think Ramsey is the one who said, if you want to calculate.
This is probably Erdos.
Right. That is. You're right. So he said, if you want to calculate R5, you can ask every mathematician, put them in a room, give them all the resources and computers, and they will eventually get it. But if you say R6, impossible.
Wow, he had a more fatalistic
Yeah.
phrasing of this. Where
Yeah,
there
with the
are- there are
aliens.
aliens.
Yeah.
If aliens appeared, who we have no possible chance to fight and could not win against, and they asked us to compute R5, we should put all of our resources towards it. And if they ask us to compute R6, we should try to fight them instead.
That's actually pretty funny.
Yeah.
That's actually pretty funny. Oh
Yeah.
my, that's a fascinating fact.
That was just a quick tangent.
Yeah, these combinatory. I have some. Well, there are a lot of things that we can talk about right now. I feel like maybe
Well-
the top things are the Galois theory, literally your research. I don't know, maybe, Or I was also reading how there's a lot of like application in like Rubik's Cube problems. And I think either we were talking before the podcast or on the podcast that Parker loves to solve Rubik's Cubes. I occasionally watch them. So, and if group theory, or I'm curious on, you know, any implications that group theory might have on Rubik's Cubes, for example. Did it make some algorithms?
Sure.
So we can talk about either or both.
So
Maybe
if
the
you
Rubik's Cube
want,
first.
you
Sure,
can think
whatever.
about like playing a Rubik's Cube is there is a group of operations, of moves that you can make. And each move does something, and you can undo it, and you can compose moves. And so this makes a group.
Right.
And then solving a Rubik's Cube means if someone gave you an element of the group, how do you undo it? And then some things you might want to know are like, what's the smallest number of moves you need to undo it?
Exactly. Right.
And we can solve these things by putting them into the structure of groups and words in groups and finding a minimal word.
But how is that really done? Like I mean, again, if you have any knowledge on the Rubik's Cube applications,
Sure.
I'm just very curious. And like,
So one way you could do
How
it
you
that
can
turns it into
minimize-
matrices
Oh,
is
like
to say, let's take this group. It's a finite group. But we can represent it in terms of matrices. So then like a quarter turn will give you some matrix so that when you take its fourth power, you get the identity matrix. And you can have 3 different quarter turns. And together, those ones plus all the different multiples that you can get, that should generate the whole group.
So what is the size of this matrix? Because you need to be able to describe 6 different colors, and
Sure, but those can just be the numbers in the...
right, but because I'm thinking you could change the position and the orientation of a given piece.
Yeah,
so
maybe
how would
let's
you?
talk about, okay, what moves can you make on this cube?
You can rotate the cube. You can
Wait,
flip a side.
Before you say rotate the cube, like you can rotate one face of a cube, right?
Right, but you can also rotate the whole thing.
Isn't that the same as, what do you mean?
Like you can take the cube and
Turn it.
turn it.
Okay, yeah, that's
Yeah.
true. Isn't that the same as if I...
Oh yeah, you can.
Actually, isn't that
One
the same if I
face
don't
at
do
it.
anything? Like if someone just like throws
Sure,
the cube to me,
it doesn't change the
it
cube.
doesn't change the cube. Okay.
But it's a move that you can make if you wanted to.
Yeah, we wouldn't put that in the group
Okay.
because it doesn't change the cube.
Okay. So you can rotate a face.
You can rotate a face,
You can rotate.
and rotating 4 times gets you back to where you started.
Yeah.
Okay. So
That's
I'm gonna
pretty
say
much it.
I have,
Yeah,
but for
that's
each
it.
face, right?
but that's the little confusing part. For each face, you gotta.
So I can have like 6 letters, and I can say, okay, I have A, B, C, D, E, F, and A to the 4 is the identity, and B to the 4 is the identity, and C to the 4 is the identity. And then I need to understand, like,
Is each letter a matrix?
each letter is a turn. Each letter is turning one of the faces.
But is that represented through like a matrix? Like if you were to
Not
apply
yet, but
if you were
it
to
will
apply
be.
the vector to that matrix, it would rotate one of the faces. And then if you apply it 4 times, it gives you back to
Yes.
where okay.
Yes.
Okay.
So we would find matrices that have those properties.
Okay.
That each one raised to the power of 4 is the identity. And then we also have to know what happens if you do combinations of them. Like if I rotate the front face and then the top face, is that the same as the top one and then the front one? And I think you can definitely
It's not.
You can say no right away.
No.
I have to maybe think about it, but it seems like if they interact at all and I do 2 of them, then it's not going to work out.
Mm-hmm.
So what is that in terms of rotating other faces? Well, like what relations are there between A, B, C, D, E, and F? And we can sort of algebraically work those out and probably like sit down with the cube and make the turns and keep track of what happens. And then we build up this little table, and then we can map it to matrices, because then we'll know how many did we actually need. Like I bet we don't need all 6 of them. You can probably not bother ever turning the bottom face. Just turn the other ones around.
Right. Yeah. You could.
So there's one of those elements that we didn't actually need.
Interesting.
So I can turn the number of generators down smaller, and that lets us pick smaller matrices. What's the actual size of this group? I'm not sure. I bet somebody knows. It's probably called the Rubik's Cube group.
Definitely, yeah.
That's some fascinating stuff, because I always wondered how. I always wondered if there was like an algorithm that would just solve for minimal time, or just like physically, mathematically. Sorry, not time, but like move wise, I guess. The minimal moves to do. So how would you really apply said operation?
I'm going to tell you again, this is another big open problem in groups. Is that we would call it a word. If you take some generators and some relations between them, that like A times B is something like C times F or whatever. If you just get a string that is the word of a bunch of letters telling you what group operations to do, and you want to know what's the smallest thing that will undo this? That's another hard problem, and we don't know how to solve it. And another one, we go, there's probably not an algorithm, but we can answer it in certain cases. This is called the word problem.
Oh, okay. It's a famous one.
It's a very famous one. We can't even tell if a word is the identity. And I mean, if we could solve any of the other word problems.
But what about, like, if you knew all of the operations, then you could just do it and see if it is the identity, or is that not possible? All right, maybe I'm not understanding what you mean by.
Yeah, when we have the generators and relations, do we really know what the thing is? It's sort of like if I have the description of the Rubik's Cube and I give you this table, but I don't let you have the cube anymore. Can you tell what the moves do?
Oh.
And here we have like a group that like didn't even come from a Rubik's Cube in the first place. Right. Like we don't know what it's the symmetries of.
Right.
We just know it follows the rules, so it must be the symmetries of something. But we don't have the object to apply it to.
And the goal is to figure out what that is?
Sometimes. I mean,
okay.
The goals are...
Goals
in math are like, figure out what we don't know.
Yeah.
And as soon as we figured it out, we go, cool, let's go find another one. It's a lot. Group theory gives us a lot of stuff that we don't know. Which makes it fun, but also makes it go, oh man, how do we not know that yet?
Yeah, I guess some things are like, wow, it should be obvious, but we don't know it. Or I think like just some parts are, I mean, my head's still stuck on the 2 to the 10. I still don't understand how we don't have an answer for that, but I mean, anyway.
No, we got 2 to the 10. We don't have 2 to the 11.
Sorry, I mean, like answer.
Maybe we do. I think something came out a few years ago. Maybe we have 2 to the 11. And it's something.
Again, you're not being cited here. It's okay. Not to worry.
Yeah, look these up.
Yeah, for sure. I think everybody knows that. Yeah, that's that. I mean, that was most of our curiosities.
Well,
do you have anything?
Of course.
Oh, of course.
Something that is up your alley, which is Galois theory that we didn't talk about yet.
So, quick introduction before. We were doing some research on this said topic because obviously we don't really know too much about group theory. And Galois' method kept coming up in almost every one of our search terms in terms of group theory. So I asked, can you talk about it? And it turns out you did your research in Galois' theory.
Sure.
So it's just perfect that, yeah. What is Galois' theory?
What's Galois' theory? So Galois was trying to work on this problem of finding roots of polynomials. And that if you have like a quadratic, there's a nice formula for it. He lived at a time when they had formulas for cubic and quartic.
That's Cardano.
So he was aware of these things. And he's building off of work of Niels Abel, who we named abelian groups after.
Right.
And the abelian groups are the ones that their operation commutes. So he was also trying to figure out what's going on with polynomials. And that there's certain symmetries that the roots have, if you think about them living in a complex space, that there's ways that you can move them around that don't change the coefficients of the polynomial.
If you don't change the coefficients, isn't it the same
It's the same polynomial,
function. Yeah.
but we've moved the roots.
Wait, what?
But how do you move
So-
How do you
the?
do that?
From the perspective of the roots, they got swapped around.
Oh, okay. So they don't. They get swapped around, but it's still the same function.
It's still the same function,
Okay.
but that tells us a certain symmetry that this function has,
Wait,
or that really like the roots have.
how is that a symmetry though?
Because it's something that we can do to it, and it looks the same.
Yeah.
We did
That's the
something.
definition.
Far-fetched. Yeah, I know. I
But that's
guess
the
that. I know,
definition,
I
right?
guess, but it's just like,
You transform it, but it looks the same. So symmetric.
like you just swap. I guess yeah, from the perspective of the roots, as you were saying.
So one way you can think about this with nicer roots is like, wait, in a quadratic case, if you look at the x squared plus 1 equals 0, you know that has these two roots that are I and minus I. So if I swapped each root with its negative, I sort of flip the whole picture over, but the polynomial can't tell. It's still just x squared plus 1.
So you are taking. So the roots of the polynomials are the elements of the group, and you're trying to find
Not
the.
exactly.
Oh, they're not. Okay.
So the roots are, I guess they're sort of like the corners of a shape. And we want to find out what are the ways we can move this shape around
Oh. So the roots
so that
themselves.
they stay where they were.
Right. The roots themselves must have already some kind of like geometric
Yeah.
symmetry
We
between
think of them
them.
living in, like, I mean, you can think of them as living in a complex space, but then we think of them as living in like a higher dimensional complex space when they don't really have nice connections. But one of them is like, okay, I would currently work on, or like recent work, is in trying to figure out things about these D4 quartic fields. That is where I take a degree 4, a quartic polynomial, and the roots have a D4 or a dihedral symmetry. That is, there's a rotation I can do with the roots to cycle them around each other, and there's a flip that I can do. And that those sort of twist each other in some way. So those elements of the group, we would say, act on the roots of the polynomial in a way that fixes the polynomial, but permutes the roots.
Interesting.
So then we classify
Yeah.
different polynomials based on their Galois group, the types of symmetries that the roots have, and then certain problems that we want to think about in terms of like, well, what if I had this root and I put it with rational numbers and I get a field? What's the multiplication like in that field? What's the basis for that field? How do we write down elements there? Those depend crucially on the symmetries of the original, on the Galois group.
So you're given a set of roots. Is the question then, what group is there in which every element of the group preserves the polynomial but swaps
Yes,
the roots?
That's
So
exactly.
every single element of the group has to.
So the
preserve.
identity of the group doesn't swap anything,
Right.
but everything else has to change something. Yes.
Okay.
When you say swap, do you mean like maybe I'm misunderstanding? Are you like saying positive goes to negative, negative goes to positive? Or are you
Sometimes.
saying
That's an example.
because, like, I was just thinking of because when you put that in my head, I was thinking of like they're equidistant from the origin or something like that. But if we let's say have a quartic where it's
But
just
this one,
shifted,
so the
and it just
the rationals, all the things there are going to stay exactly where they were. All the coefficients of the polynomial stay exactly where they are.
right. But my question is simply like if you shift it.
Shift what?
Like if you shift the graph, right, then the roots, I'm just like let's say they're all positive roots, for example. So when you say swap the roots, do you mean like the first root and the second, like
I sort of
what does
mean
that
like
even
first
really
and
mean?
second.
Yeah,
and I
Yeah,
switch
what does that
them to
really
second.
yeah.
mean when you
Like-
say that?
like, let's
You're just
say-
swapping them
let's
literally.
When I
say-
do it notationally, I write a little sigma 1, sigma 2, or zeta 1, zeta 2, and I literally just switch them.
But it's the same thing.
Yeah, exactly. But let's say you have a quartic, and the roots are 1 plus I minus 1, minus I minus 1, and 1 minus I. Like, the four corners.
Then that's like 6.
Then in that case, you know, you can just multiply them by 1 minus 1 I minus I. The roots will stay the same, you know, they'll just all swap. Does that make sense?
I mean, I'm just thinking, that specific example would make sense. I'm just thinking of, my brain.
Part of what makes this hard to think about is that, like, the things that we're familiar with, like degree 2 polynomial, there's only one group of order 2. So we know exactly what it's going to be.
Because it's prime.
It's prime. And then for 3, well, there's 2 different possible groups it could be. One of them has 6 elements in it. So there's sort of, you have this degree 3 polynomial, but you can't even see all of the symmetries yet. They live in some higher realm.
Wouldn't there also be one group
Say.
for...
There is one. There will be a cyclic, yes.
It's just one.
So there's certain polynomials, if all of their roots are real and they behave in some nice way, then you can rotate what the roots are cyclically and get the same polynomials out.
So what are like some common examples of, because you were mentioning how they're called
Yes, these are Galois groups of
Galois
polynomials.
groups. So like, could you give some example? Like, I mean, I guess you mentioned cyclic, but maybe if you put some more examples in my head, I'll maybe understand.
So
a
the
little
ones
bit,
that we think about a lot are the
what are-
cyclic groups. The symmetric group is like the biggest it can possibly be. The symmetric group means take all the possible permutations. The alternating group, this one is taking like half of the possible permutations.
Right.
And the way that you might think about it is sort of like, if you take the real numbers and you remove 0, it kind of has 2 parts. It has a positive part and a negative part. And the alternating group says, just keep the positive part. Ignore that other second half mirror world. Don't worry about that. There's sort of another copy of itself that doesn't have the identity 1 in it. It has like a -1 where everything is backwards.
So you're saying those.
So
could
the
be
alternating
groups of
group is a
these
big one. The
roots.
dihedral groups are the ones that I would work
Yeah, right.
in.
You just mentioned that as well.
But
these
there are other
groups
ones.
of-
As the thing is, when you get bigger sizes, you get more possibilities of groups. And Galois groups can't be anything. They have to have certain nice properties.
Oh, so they're not just in general.
It's not any group can be Galois group.
Right. Which makes sense because there's a huge restriction on what the
fact that it
Galois
has to be the
group
same
has to do,
polynomial
right?
and whatnot, Right.
Yeah.
Of
Yes.
course.
Yeah.
But I'm assuming that also makes the. I mean, correct me if I'm wrong, but doesn't it make the computation easier?
Yes.
Right, because you have so many restrictions.
I can tell with a little computation what the Galois group of a polynomial is, as long as it's at most 5.
Oh, that's actually a.
Interesting.
That's a
I mean,
skill. Put
that's
on your
not.
resume. I can tell Galois groups.
There's a few tricks. I know some tricks, and I can take some discriminants,
That's
and I can
interesting.
check certain traces.
So what does it look like to do research in this? Is it a lot of coding? Is it a lot of
There
just
is a lot of coding.
writing down things?
It
and-
is a lot of writing
Okay.
down things and drawing pictures and
Okay.
trying like talk to other people and go like, I don't know what's happening here. Is this something? I did all these calculations. Is this meaningful? Does this tell us something else? And then a lot of reading. Like a lot of it is, what did people figure out already? What's current? What did someone like just recently write about? So right now, I'm reading through this paper by Ila Varma and Errol Shankar at U of T and a few other people.
She was last year for 224. She was
Yes.
a lecturer. Yeah.
Yeah, Dr. Varma and also Dr. H. They are all big in this. They do more stuff in Galois theory and these things about counting, like what happens in these spaces, trying to figure out how big are they? What's the volume? How come the volume doesn't really match up with the number of points we would get? Shouldn't it? Weird.
Wow.
So shapes.
Shapes.
Shape stuff.
Yeah, when I asked Google to define a group, it said,
ChatGPT.
Yeah, well, all right. Well, specifically, imagine you have a collection of geometric shapes. Like that's literally how it was defined, just to help the understanding of it. So, I mean, that's how I think a lot of the explanations are also going. You know, think about analogous to a square and then do the same thing. But obviously,
you're not doing it on that. Maybe.
No, we're doing it on that.
Oh,
I think of it like I put
Like a
this
literal
square on
square?
the. Where do these points? When I do some computational thing, I can plot the points in space. And if they don't make square shape, I know it's not dihedral. They have to do certain things. I know that a flip will be complex conjugation.
Could we maybe discuss about some applications, like
Oh,
real
boy.
life applications?
I think
of
literally
these
everything.
groups?
It's
I know,
certain
yeah,
like
I'm
group
really curious
theory
now.
is so fundamental to anything that we're doing. In terms of like, if you use matrices and you want to multiply them, this is relating with groups. And we are using things that we know about groups in order to be able to write down every matrix concisely and represent it in a certain way and tell when two things are the same or different.
So do properties about groups tell us things about matrices as well? Like, for example, if you have like properties of symmetric matrices, let's say you define a symmetric matrix and no one else knows about this. Is there something you can go read about group theory and say, oh, these should have this property because groups?
Yes, for sure.
Okay.
A lot of stuff, hit it with the hammer, right? Group theory is a big hammer and has a lot of theorems.
So a lot of things trickle down from group theory that most people,
Pervasive.
right? Most people won't really trace back to group theory, but
Sure.
that's where, or I guess maybe it could come from one step higher, but for now we'll just call it group theory.
Yeah, I feel like it just represents, because I feel like the actual use cases of it, you're just mentioning how we anyways do things with it, but they're just representing what we already know. Like we anyways are rotating the square, but this just tells us that, hey, when we do it, it's symmetric. Like, I don't know, does that question make, or does that statement make sense? Like, to a certain level, it's not really doing anything actively, right? Like group theory is not really doing anything. It's simply stating what's already there. It's just in a higher sense.
I suppose. I mean, it is
really-
describing a structure, but a lot of times it reveals the structure we didn't know was there.
Right, I guess in some situations, we were talking about the triangle and whatnot, like there are some situations where it can actually reveal things.
Now, if you want, it also does make like little inroads into other places and say things like representation theory is trying to figure out what's going on inside of a group by using matrices and vector spaces. And then it happens to tell us a lot about fundamental physics particles. And we go, we didn't know why, but it seems to be related to this big group. Better investigate that group some more. What's going on in
Yeah.
there?
Well, a lot of group theory has been understood today, I think. At least, I mean, compared to what we knew, which was nothing. I think at least the basics, because I think when a lot of people hear things like group theory or things like graph theory, I don't know, I just put two theories together there, but or any real, even though it doesn't sound very complicated, they immediately associate it with, oh, you know, it's this much higher level of understanding that is required.
We don't tell you about it in high school. It's secret math.
It's like algebra, but more useful is basically as we start.
Well, define useful.
Okay, yeah, that's a good point.
I mean, we
That's
need
a
them
good-
both,
That's
right?
a good point. Right. No, that's a good
Group
point.
theory puts a lot of ties between geometry and algebra, which is great. Then, like, we can describe groups geometrically, we can describe them algebraically.
That's actually a wonderful way to put it, because geometry and algebra is group theory.
That's
You know,
that's a common
you know,
language for them both.
Phenomenal. That's actually a really nice way to wrap that, because I feel like a lot of people would still have, you know, some surface level misunderstandings of, because I don't know, when I first heard the word group theory, knowing nothing about it, I just thought that, okay, it's going to be something that I have no idea, because when you think of groups in math, or again, not that I knew anything, but sets of elements, and then you're operating on those sets of elements. Like, again, it's all so abstract. I mean, to a point similar to algebra, it's all so abstract. Oh, find x in this triangle. Like, what am I doing that for? You know, like, it's all so abstract that you really start to question, well, what, like, am I even learning this for some practical purpose? But then it's good to know that at the end of the
We're
day,
getting like the really refined version
Yes,
after
exactly.
150 years and a lot of iterations.
yeah,
And I would say, yeah, go like play with some shapes and stuff, and
Yeah.
like multiply some matrices. And see,
yeah,
what if I take a 2x2 matrix and I put ones on the diagonal, and I put a 0 below the diagonal, and I put some other number in the top right, and I multiply matrices like that together? What does that do? Can I predict what's going to happen? And that's going to be a group. All those things are invertible. What's the inverse of something? And do this with 3x3 matrices. And do this with other objects around.
yeah. I guess like the connection to objects is what sometimes might fascinate people, but also confuse people. Because when you say, you know, rotate a square, you're like, oh, okay. Or, I mean, I guess in certain cases, but when you actually apply math, or I guess rotations is pretty understandable. But I'm saying any other type of group to certain objects, it can be a little more, I don't know, is it a little more confusing than when you operated with numbers?
Well, I mean, if
right?
it helps, like, we are very confused about it also.
Well,
Like,
Yeah.
it's good to know that you
we
guys
don't
are
know
also
what the
confused.
groups are.
Right. It's also good. Yeah.
It's hard.
yeah. Yeah.
We stick to the real shape stuff, right? I'm going to look at dihedral groups because I know what that is.
Right.
And only up to 4 because we don't know. We don't know what's going on in these other, anything higher.
Right. Well, any more curiosities for you?
Yeah, I think this is a good place to end it.
Yeah, I
Where
think
a lot was
that-
discussed.
Yeah, a lot was
So.
discussed. A lot was understood.
Wow.
I think that Matrix game was fun. Just learning that hey, they're the same.
Go and play this Sudoku, build
Yeah,
a
right.
group.
Oh right. I mean, anybody can do this at home. By the way.
Try to
right?
get
The
some
same
for
thing.
6. Try to get some for 8. 8 is a really hard one. I almost made it a problem in a course, and I did it myself. I'm like, too hard. This is too hard.
Okay, so maybe not 8, but you know, just mess
But
around.
no, try
with
it
other
anyways,
matrices,
it's
Why
fun.
not? I mean, they always can. So yeah.
Yeah. Thanks for coming on the podcast again.
Oh,
Thanks for
always
It's
having
lovely
always
to have
great.
You. Always lovely to have you. Always love it because, as I said at the beginning, brains are always picked. So, always learn something fascinating. So, yeah, thank you. Hopefully, we have you on again for
Something.
Name your topic.
Something.
I'm sure we can.
If it's some beyond high school
Oh, right.
at
course.
university level math,
Yeah.
I got some things to say.
Okay,
Yeah, I
cool.
mean, as you know, you have our contact information. We're always very excited to have you on whenever you want.
I think
And-
the next math episode should probably be topology. We haven't spoken about
Okay.
topology
That's
yet.
something
so
I know nothing of.
there you go.
So why not? Okay.
More shapes. And we got a coffee mug already.
Yeah.
Yeah, I mean, a donut is a cup, right? So
You know a lot about
Right.
No, we
topology.
do. We
Yes, I
do.
do.
Yeah.
So that would be a very interesting episode. So
Yeah.
yeah, actually, that's a good idea.
Yeah.
Maybe
There
we
you
can
go.
do that soon enough. Yeah. So yeah, once again, thank you so much for coming on.
Yeah. Thank you to everybody who's listening. Make sure to rate us 5 stars on Spotify. Why not?
Why not?
Why not?
On
And,
YouTube too, you know, hit that like button, comment down, or Apple or wherever you really listen to it. Why not? Have
Wait, you
fun
got a
with it.
comment of the week?
No,
No, we actually don't.
Don't have a comment of the week this week. 'Cause,
Comment of the week is there's no comment of the week this week.
yeah, a little unfortunate. Already explained before, but yeah, it should be good. So yeah, I think that calls it.
Thank you so much, everybody. This has been episode number 110 of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we'll see you soon.
Bye, guys.
See ya.